Binomial distributions involve a random variable that can have a success or failure as its outcome. Before we link up probability with combinations in Pascal's triangle, I want to consider an example from polynomials. Expanding the binomial x plus y raised to the third power using the definition of exponents gives us the following product, and then we distribute the first two binomials. I'm intentionally not combining like terms, and now I will distribute further, creating this series of terms, and do the last distribution to create this string of polynomials. What you'll notice is the color coding of like terms. There are three of them here, so then that's why this coefficient is 3 when I combine like terms. But notice you could rewrite the fact that these are three terms. The order of them doesn't matter. And so when I arrange them, that's the same thing as taking their combination. And there's only one grouping of this, so that's 3 choose 0. There's only one grouping of this, so that's 3 choose 3. And so we're starting to see a parallel with combinations and these coefficients of binomial expansion. In the past, we've used Pascal's triangle, which relies on the above rows to create the next terms. And the way you do that is by taking the number above, adding them together to get the number below. And so they correspond to the coefficients of expanding a binomial, so raising it to higher powers. And you'll notice that these coefficients correlate directly with using combinations, which is summed up as the binomial theorem. You could use a calculator to compute these coefficient values like 3 choose 2, or you could use this formula. What's nice about and an advantage of using combinations instead of Pascal's triangle and a power of the binomial theorem is that Pascal's triangle requires you to create every single row up to the one that you need, and if you removed a row above it, the triangle would fall apart because they're linked together kind of like a spreadsheet, whereas the binomial theorem allows you to pick out just the combination that you need in order to find that coefficient. To put this new connection into practice, we will use the binomial theorem to expand each binomial. The binomial theorem gives the following expansion of 2x plus y raised to the third power. Notice that the coefficients in blue are now replacing how we would use Pascal's triangle. And since the power of the binomial is 3, that's the n value of the combination. And this is the first term, so you start at 0, and then so this starts at the power, this starts at 0, and then the first number always stays the same, and then the second number, how many you're choosing, is always increasing by 1 until it equals the n value. And then you take the first term in the binomial and you raise it to the power equal to that of the original. Make sure to use parentheses. And then you take with the sign of the second term in the binomial and you raise it to the 0 power. And then these exponents will exchange. So as the first term descends by 1, the second term will ascend by 1. As you can see in blue, 3 choose 0, or how many ways can 3 items be put into 0 groups? 1 way. How many ways can 3 items be put into 1 group? 3 different ways. And down the line, giving these coefficients and then simplifying to the following. The following example will be handled similarly. Because there is a subtraction, every other sign will alternate, starting with the second term. That is because I will be raising a negative to an odd power, which makes a negative. Using the calculator to find these combinations written in blue, we get the following binomial in expanded form. You can confirm this result using Pascal's triangle. Similar to how combinations apply to polynomials and their terms after you expand them, because when you arrange like terms, their order doesn't matter, you could do that with binomial experiments. Consider the following. Let's say you have a spinner. A quarter of it is green, 3/4 purple. And let's consider the probability after 3 spins of rolling or spinning one time that it lands on green and then the other 2 times it lands on purple. So then this would be part of that sample space. So I could get green on the first try, which has a 1 in 4 chance, and then purple on the other 2. Or I could get that success of landing on a green the second trial of the 3, or of the third spin of that trial. So then the probability that occurs is provided by the following formula. So I do 3 choose 1 because of the 3 outcomes, I want one of them to be a success of landing on green. And then because these events are independent, each time I flick the spinner, the previous attempt doesn't affect the current attempt, then I multiply each of these probabilities together. And so that's why these are all multiplication here. And that only occurs once, so then I'm only choosing one success. These numbers are always the same. And then I have 2 of these 3/4 multiplied together, so then that's n minus r, 3 minus 1, or 2. So that's where this formula comes from, noting that r here and there are always the same. P is always defined to be the probability of success. Q is the probability of failure. And given our successes, this is the formula. So please note that the sum of the probability of success and failure always equals 1 because they are complements of each other. Jean usually makes 2/3 of her free throws in basketball practice. Today she tries 3 throws. What is the probability that Jean will make exactly 1 of her free throws? Success is defined as making a free throw, and there's a 2/3 chance of that occurring. So that is the p value. And its complement, q, is 1/3. And this will count as a binomial probability problem because you either make the basket or you don't make the basket. So we want to know the probability that Jean will make exactly 1 of her free throws. So have 1 success and 2 failures, which creates the following sample space. So this is the space of all possible outcomes. So 1/3 times 1/3 times 1/3 represents that Jean makes no free throws because Q for failure will occur 1/3 of the time. So here is the probability that she misses all 3. And then here she makes 1 of the 3, 1 of the 3, 1 of the 3. So that's exactly what we're looking for. And then these other ones are the other possible outcomes that we're not interested in. Because we have these 3, that's where the combination comes in from this formula, because their arrangement order will not matter. And then we have to multiply the number of successes and the number of failures. So we have 3 choose 1 times 2/3 times the quantity of 1/3 squared, which gives us the following probability. So 22.2% of the time, Jean will make exactly 1 of her free throws. Let's consider the question, what is the probability that Jean will make at least 1 free throw using this sample space to guide us? So here we find this, and all the way would answer this question. So the way that you solve it using the binomial probability formula is by saying, well, if she makes at least one free throw, that's the same as saying she makes exactly one, plus the probability that she makes exactly two, and the probability that she makes exactly three. So 96% of the time, Jean will make at least one free throw. Calculating three separate probabilities doesn't take too much work, but there is an easier way to solve this kind of problem. Use the complement. How about Jean will make no free throws? And we find that we arrive at a similar answer. We will now use binomial probability to solve the following problem. If you make 4 trips to a drawbridge, and if there is a 1 in 5 chance that the drawbridge will be raised when you arrive, what is the probability that the bridge will be down for at least 3 of your 4 trips? This one is tricky. The problem is asking us to find the probability that the bridge will be down, which makes sense because then we will get to drive through. But notice that the probability is given as a 1 in 5 chance that the drawbridge will be raised when you arrive. So we need to have consistent wording. So let's translate a 1 in 5 chance that the drawbridge will be raised to a 4 in 5 chance that the drawbridge will be down. And then let's translate the idea that the bridge will be down for at least 3 of your trips, meaning that r can equal 3 or r can equal 4, so we get the following formula. So success is defined as a drawbridge being down, which there is a 4 in 5 chance of that happening, and I want 3 of those to occur, and its complement is 1/5, and I only want 1 of those to occur, and then all 4 times successfully driving without having to stop because the bridge is up is represented by that, and so you get the following answer. So using binomial probability, we find that 81.9% of the time you will not have to wait when driving across that bridge. So in this lesson, we covered binomial probability, which is going to be a type of problem where it could either be a success or a failure, and you need to use multiplication because each trial is independent, and combination is involved because the arrangement of the successes and failures is irrelevant as long as you get the result that you wanted.